I've been a little bit crappy. Okay. 5.2, and this is kind of where the unit gets serious. I tend to think of this unit as not super difficult, but the last couple semesters people have struggled a little bit with it if they don't stay on top of it. I think in the scenario we're in, you guys will do okay because you have your notes with you. You can see all the formulas. It's very heavy formula based, and as long as you can plug numbers in, you'll be okay. Okay, the binomial theorem is going to look like this. The binomial theorem is basically a theorem that allows you to expand binomials. That's why it's called a binomial theorem. So a binomial is just two terms being added or subtracted. So we're going to take two basic terms, A and B, and we're going to add them together and look at what all the expansions look like. So the expansions mean if I have them to some exponent, and I'm just going to increase by 1 each time, what does the answer look like? So we're going to start right at the beginning, and I've purposefully coded this in red and black so that we can see the patterns. So the first thing we want to look at is what happens when you have anything to the exponent 0. Now it doesn't matter that's a binomial. It wouldn't have mattered if it was a monomial. It wouldn't have mattered if it was a trinomial. Anything to the exponent 0 gives you an answer of 1. Okay, so that one was easy. I didn't have to think about that. Now the next one, thank you, Benji. Oops, chip snack. The next one, which is to the exponent 1, I'm going to keep increasing the exponent by 1. Now anything, again, doesn't matter if it's a monomial, binomial, trinomial, anything to the exponent 1 is just what was inside. So I'm going to write this a little different. Instead of writing a plus b, I'm going to write 1a plus 1b. That's going to be the answer here. And you might be saying, okay, go ahead, open them.
Got it.
Okay, good.
Got it.
So you might be saying, well, why are you writing it way over here? Well, I'm writing it way over here so that I can get this triangular pattern. The reason I want a triangular pattern because this is going to link directly to Pascal's triangle. Okay, so now as I go ahead, they start getting more difficult as I go to the next one. So a plus b squared is the idea that you are going to do a plus b times a plus b. Well, this is, you first learned this in grade 10 when you were doing binomial expansions, and you used a method called FOIL to expand it out. So you did a times a times b times a, b times b. Don't worry, that's not coming back. I need you to understand it here, but I'm not going to ask you to expand binomials. Okay, so when you actually do the FOIL, you get this answer. A squared, 2ab plus b squared. And again, I'm going to write it with 1. So 1a squared plus 2ab plus 1b squared. Okay, then I go to the same binomial cubed. Well, cubed means I'm doing the squared one multiplied by another a plus b. Okay, so I'm going to put the a plus b here and then put the answer to the squared one. Now you have to distribute that all out. 2, 3. You're going to get tons of terms, and you're going to get this as the final answer. 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. And you're saying, well, that's a lot of work. Yeah, that's a lot of work. But what if I told you I could go to the next one, which would be, 5, 6, 7 lines of math. And I could look at this and say, I know for a fact that the answer is this. 1, a to the 4 plus 4, a cubed b plus 6, a squared b squared plus 4, a b cubed plus 1 b to the 4. How would I know that? This is something that you're supposed to distribute. A plus b times a plus b times a plus b times a plus b. This is something that would take you half a page. What if I said, well, I can also tell you what a plus b to the 5 is and a plus b to the 6. I could tell you what a plus b to the 17 is right now. In one line, I could tell you what a plus b to the 17 is. And this is the power of what we call the binomial theorem. And the binomial theorem, all these red numbers that are appearing, what we would call the coefficients, come directly from Pascal's triangle. You will notice that everything in red here is Pascal's triangle. Okay, so the coefficients come from Pascal's triangle. Okay, that's the first thing that we need to be aware of in what's going on with the binomial theorem. The next thing we have to be aware of is these A's and B's are not kind of flukes either. There's a pattern there. And you'll notice if we look at this 0th diagonal here, in the first one there was no a. Then it was a to the power 1, a to the power 2, a to the power 3, a to the power 4. And what expansion were we doing? we were looking at expansion to the power of 4, and this one was a to the 4. Expansion to the power of 3, this one was a to the 3. Expansion to the power of 2, this one was a to the 2. So you're starting to see a pattern there, and then look what happens to the a's. The first term had an a to the 4. The second term has a cubed. The third term, a squared. Fourth term, a. Fifth term, there is no a. What's happening is the exponents on a are decreasing by 1 as you go forward. Okay, exponents on a decrease by 1 as you move in that direction. Okay, so that's another pattern. The exponents on a decrease by 1 as you go in that direction, and they also happen to start at whatever you're expanding. What else is to know is what's happening with the b's. Well, there is no b here. Could be seen as b to the 0, because what's the answer to b to the 0? 1. Then it goes b to the 1, b squared, b cubed, b to the 4. It's doing the opposite of what the a's are. So you can also say that the exponents on b increase by 1 as you move forward. Okay, so these are a couple interesting facts about what's happening when you're doing a binomial expansion. This is called the binomial theorem. And we are going to start to directly link these values of Pascal's triangle to something we did in the first unit, something called combinations. Do you remember? Choosing and choose R. So we're going to start to see how this all kind of plays into a probability model and how binomial theorem and Pascal's triangle are all linked. Okay? So just be aware, what I've shown you so far should be the beginning of the lesson from grade 11, 11U. If you took 11M, I have no idea what was on that class, I've never taught it. But 11U, this should all be of no surprise. This is a refresher, you kind of remember looking at Pascal's triangle. Okay, now, I want to show you more how this applies to this course. So, as we go across here, what I want you to realize is there's a direct link between the numbers in Pascal's triangle. I'll do those in red again that we just did. 1, 1, 1. Etc. Actually, I'm going to erase that last line. I don't want to go that far. Okay, that's the beginning of Pascal's triangle. And if we want to look at what this means in terms of combinations, so this is on your sort of second slide that you have. This, remember, was called, let's just look at what this was, term 0, 0. This was called term 1, 0, term 1, 1. So this is based on what we learned yesterday. Etc. Now, these were n values and r values, n value and r value. This is talking about, the first value is talking about the row number. This is talking about the diagonal number. What it also applies to, if I take the row number and the diagonal number and put them into a combination, I will get the exact same answer. 0, take 0 items and choose 0, you're going to get 1. Take 1 item and choose 0, you're going to get 1. Take 1 item and choose 1, you're going to get an answer of 1. So, in fact, all of these values in Pascal's triangle come from combinations. Okay, so I can build Pascal's triangle same sort of way. This black line's kind of in my way, but I also kind of need it. Like this. Okay, so this becomes 3, choose 1. Oops, 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3, etc. Okay, so as you go across, the numbers that we looked at yesterday that appeared in Pascal's triangle are in fact combinations, which are just numbers also. But if you took your calculator and you said, well, I'm not sure what 3, choose 2 is, and you typed in 3, choose 2, you would get 3. Oh, 3, choose 2 is the same as this 3. So now we have 3 ways of looking at how Pascal's triangle is formed. We can look at straight the numbers, the combination equivalents, and the terms, which talk about row number, diagonal number, row number, diagonal number, and so on and so forth. Okay, so in general, we kind of say that this is n choose r, where n is the row and r is the diagonal. Okay, and this is how we are going to start to assess what's going on in Pascal's triangle in terms of a general form for us to use the binomial theorem. In grade 11, we always had to reference Pascal's triangle and pull the numbers off. Now that we've learned about combinations, we don't have to do that anymore. Okay, so where are we going to get? A couple properties we want to talk about first is the same sort of addition property. So yesterday we learned that if we take term nr, then we can find that by going to the row above it, n minus 1, and the diagonal before that. So this was the general term that we had yesterday. We're going to use that exact same identity and apply it to the combination form. So now we're saying n choose r, okay? Same as here. We said this is term nr. Well, this is n choose r is going to be equivalent to n minus 1 choose r minus 1 plus n minus 1 choose r. Tap a tile above to reveal the letter. That's giving you a clue, I think. One of those tiles. Okay, so this is one way to look at it. Also shown on your sheet, same sort of thing. If you take nr and add it to the next one in the row, nr plus 1, you'll get n plus 1 choose r plus 1. Either one of these formulas works out the same way. Okay, go in the same row, row n, take diagonal r plus 1, and you're going to get the n plus first row, diagonal r plus 1. Okay, so basically how you apply that is if you're actually doing an example of this, it's not overly difficult. You do something like, okay, if I have 4 choose 2, and I want to add it to 4 choose 3, in the fourth row, the second and third diagonal, if you added those, it would go down to the next row, the fifth row, keeping the larger diagonal, 5 choose 3. And if you actually figured out what these numbers are, this is 4, this is 6, and that's 10, and you would go about your business, and it would be completely fine. Okay, so that's one of the properties that you want to look at. And the other property that we should sort of talk about is the fact that this was symmetric, right? So these values have to be the same, these values have to be the same. As you go across here, values on either side always have to be the same, right? So this is the property that whatever n choose r is, say that's n choose r, it has to be equivalent to the one that's on the other side, which is n choose n minus r. Okay? And so the idea here is, if we looked at a couple examples they had on the sheet, is if I have 9 choose 3, it will be equivalent. This is now 3 in from the outside, right? There's going to be 9 choose 0, 9 choose 1, 9 choose 2, 9 choose 3. It should be equivalent of 3 in from the other side. If I subtract 9 and 3, I get 9 choose 6. So those are equivalent on either side of the symmetry. And it applies to anything. If I said, okay, well, use 27, choose 12. How do I know what that's equivalent to? Well, these numbers down here just have to add to the top number, or you can subtract. 27 minus 12 is 15. Okay, so that's the other property that's sort of useful. Okay, so all this seems a little bit tricky. You're going to have to practice to get the hang of it. But the main goal we haven't even looked at yet of 5.2. Okay, the binomial theorem itself is what we're getting to, and that is what I'm going to look at right now. So the binomial theorem is something that helps us do those expansions easier. The binomial theorem is why I knew how to do a plus b to the 4. Okay? And we're going to use it with combinations because we've learned that in this class. And we're going to apply those patterns that I already looked at. So if I wanted to, this is the binomial theorem. A plus b, a and b can be anything, to any exponent n, is going to start like this. Whatever your expansion you're doing, you're going to do n choose 0 first. a to the power of n. Remember when I was looking at those patterns, I said, oh, in the fourth row it started a to the 4. In the third row it started a to the 3. So in the nth row it's going to start a to the n. Remember the first one had no b value. Well, now we have to go to the next term. Well, if the first value in the row is n choose 0, remember this is the nth row, the 0th diagonal. We're going to stay in the nth row the whole time. But what diagonal do we move to? The first diagonal. What happens to the exponent on the n? It goes down by 1. What about on the b? It goes up by 1. So this was really b to the 0. This becomes b to the 1. And then we keep going. Stay in the nth row. We are at 0th diagonal, first diagonal, second diagonal. Now the value on the a goes down by 1 again. It's now n minus 2. And this becomes b squared. And then you continue to go. You will go all the way until you get to the very last term. In the nth row, it's going to be the nth diagonal. There will be no a value because you will have run out, and you'll have b to the n. Okay, so this is the general formula for a binomial expansion. Okay, it looks complicated. It is not. The one that we did that's on the sheet here, it says, well, how would I do a plus b to the 4? Well, in this case, we now know our n value is 4. So it becomes 4 choose 0, a to the 4. Then in the next one, 4 choose 1, a to the, remember what happens to the a's? They go down by 1, 4 minus 1. So it just becomes a cubed with a b. Continue this pattern, 4 choose 2, a goes down by 1, so it now becomes squared, b goes up by 1. This was b to the 0, b to the 1, b squared. You were at 4 choose 2, you get to 4 choose 3. A goes down by 1, it's now to the power of 1. B goes up by 1, b cubed. And then the last term is always when you choose yourself. So in this case, 4 choose 4. A goes down by 1, that's a to the 0. You don't need to show that. B goes up by 1. Okay, and that's generally kind of what's happening here in terms of what's going on. Now, if we apply this and said, okay, could you do a plus b to the 6 in the same way? Of course. I would do 6 choose 0, a to the 6. 6 choose 1. Just keep increasing this. What happens to the power on the a? Goes down by 1. What happens to the power on the b? It was a 0 here. Goes up by 1. 6 choose 2. A goes down by 1. It becomes a 4. B goes up by 1. 6 choose 3. A goes down by 1. B goes up by 1. And then you have to keep going. How do I know where to stop? When you choose yourself. So I go to the next one. 6 choose 4. A squared, b to the 4. And the last one will be 6 choose 6, b to the 6. So is it a lot? Maybe. Is it a pattern? For sure. Will we have to calculate these combinations eventually? You bet. Okay, so it is a little bit time consuming, but the pattern remains the same. Some things you should note. Every time, what do the exponents on a to the b add to? 2 plus 4 is 6. 1 plus 5 is 6. 5 plus 1, 4 plus 2, 3 plus 3, 6, 6. They all have to add to your n value. If they don't, you've made a mistake somewhere. Okay? Now, the next...
When you're going to be done it?
Pardon me?
When you're going to be done it?
I'll be done soon. The next examples are going to apply to things where we don't have just a and b here. I have actual values. Okay, so I'm going to leave the general formula up there just to show you what's going on. And the only way you're going to get better at this is by practicing or following the pattern when we do the assignment. So it's not really written on here so much. The one on here is quite difficult, so I don't know if that's the best one to do right away. Let me make one up. Okay, I'm going to do x plus 3 to the power of 4. So we no longer have a's and b's. We have values here. But what you can basically say is our a value is an x. Our b value is a 3. Our n value is a 4. So if you follow the same rules, you're going to be able to then simplify it and make your life a little bit easier. So Again, if it's the power of 4, you start 4, choose 0, a to the 4. Well, in this case, our a is an x. So I make it x to the 4. Then I move on to the next one. 4, choose 1. What happens to my exponent on this? It goes down by 1. Now I introduce my b value, which in this case is a 3, and it's to the exponent 1. Okay? Sorry, I don't have enough room. So then I would go, okay, and I can move up to 4, choose 2. What happens to my exponent on my x? It goes down by 1. What happens to my exponent on my 3? It goes up by 1. 4, choose 3. Exponent on my x goes down by 1. The exponent on my 3 goes up by 1. And then my last term is 4, choose 4. Exponent on x goes down by 1. It disappears.
Mommy,
And I have 3 to 4. Yes, Morgan.
how do you spell danger?
D-A-N-G-E-R. Okay, now here we have to actually go through and simplify these. So what we now have is 1, 2, 3, 4, 5 terms that we have to calculate. You'll note that every time you do an expansion to a specific power, there's always one more term than the expansion you're doing. So expansion to the power of 4 has 5 terms. If you were doing expansion to the 17, it would have 18 terms. To the 35, 36 terms, always one more. So what you have to be able to do at this stage is actually do the calculations. So if you have a calculator, you can use your combination buttons. Okay, when you do 4, choose 0, you get a 1. So this is really 1 times x to the 4 is 1x4. When you do 4, choose 1, you get 4 x cubed. What's 3 to the 1? 3. So I'm doing it kind of in 2 stages here. I'm going to first simplify each thing individually, then I'm going to do the multiplication on top.
I'm on page 50.
Good boy. I'm almost done. Keep reading.
Good.
Okay, 4, choose 2 is 6. You have an x squared. Well, what is 3 squared now is 9. That all has to come into play. Okay, so 1, 2, I've done 3 of the terms. The next one, 4, choose 3 is a 4. X I'll leave there. 3 cubed is 27. And then my last term, 4, choose 4 is 1. 3 to the power of 4 is 81. So you'll notice I am breaking it down. I'm simplifying it a little bit. But I still have 5 terms. And now I just do the last calculation. Can I do anything with 1x4? No. But this one, I have a 4 times x cubed times 3. You remember multiplication doesn't matter what order you multiply things in. Obviously, we need to multiply the numbers, so you can't do anything with the x cubed, so it just becomes 12x cubed. Multiply the numbers, 54x squared. Multiply the numbers, 27, 54, 108x. And then the last term is an 81. So this would be the full binomial expansion of x plus 3 to the 4. And that's the power of the binomial theorem. Because if you had to actually do x plus 3 times x plus 3 times x plus 3 times x plus 3, you would be doing distributive property over and over and over and over and over again, and it gets pretty ugly. This, if you're good, you can do in 2 steps. If you want to go slowly and do one calculation at a time, you do in 3 steps. None of them are more than 3 steps though. And never do I give you one that's, greater than the power of 4, maybe the power of 5. Okay, so this is sort of the idea of how this works, and this is the main goal. This is what you're going to be assessed on. Can you use the binomial theorem by applying the combination version of Pascal's triangle, and then the patterns on A and B. Okay, the one they have, and that I have in this note, which is rather difficult, but I'll show you what it is anyway, is, what exponent is that to? Oh, find the first 4 terms. Okay. Example 5, it is written in here as, find the first 4 terms of this expansion. 2x minus 3 over x squared to the 8. So there's a couple sort of ugly things about this one. First of all, let's assess that our a value is 2x. Our b value, and this kind of encompasses everything, so it's good, is a negative, so be aware of that. It's a negative. So you have to include that negative. Negative 3. Now we can write it as 3 over x squared, but it's easier if you get rid of the denominator. So now you have to remember exponent laws that say if you have a value in the denominator to an exponent, you can move it up to the numerator and change the exponent to a negative. So that's really what our b value is. Our n value is 8. Okay? We just want to find the first 4 terms. So when we do, what's that? You can jump down, yeah. I'm almost done. When you do this expansion, you're simply going to look for the first 4 terms, not all 9 terms. Remember, if you're doing an expansion to the power of 8, it'll have 9 terms in the answer. This would be a massive question. Luckily, we're only doing the first 4 terms, so you'll kind of work it in the same way. So if your n value is 8, you're going to start with 8, choose 0. Then you take your a value, which is 2x, and do it to the exponent 8. There is no b value in the first term. Then you move to the second term, which you're going to make 8 choose 1. The exponent on your a goes down by 1. It's now a 7. The exponent on your b will be a 1. Okay? You then move to the next term, a choose 2. Again, the exponent on your a goes down by 1. It's now a 6. The exponent on your b is now a 2. And then your last term, I have no room for any of this. Only because we're trying to find the first 4 terms. 1 term, 2 terms, 3 terms, 4 terms. Exponent on my a moves down by 1. The exponent on my b moves up by 1. Some things you can check. What do these all add to? 5 and 3, 8. 6 and 2, 8. 7 and 1, 8. Okay, a couple things. So if they asked you to do this, you would get... Yes.
Can you switch over?
No, I can't. You would... Morgan, I'm almost done. You would get 2 marks out of 4 for just writing this part of it. Because you applied the idea of combinations, you applied all the patterns correctly. The other marks you'll get are for actually simplifying all of this. Okay, and simplifying can be difficult for some of you that don't have strong arithmetic and algebra skills. So take your time, go through it. You have the luxury of time in this course now. So again, on your calculator, if you need to do 8, choose 0, you'll find 1. Exponent laws say that if you have an exponent to a product, like 2 times x, that exponent has to apply to both. So you're going to have 2 to the 8, and you're going to have x to the 8. So maybe you do it all in one step right now. You say, well, what is 2 to the power of 8? Well, 2 to the power of 8 is 256. X to the 8. That all came from that first term. Okay? When I go to the second term, 8 choose 1 is 8. And I'm doing the same thing. Well, 2x to the 7, the 7 has to apply to both the 2, so that's 128, and the x. But also on this one, I have times negative 3x to the negative 2. So that's going to have to apply at some point. Next term, 8 choose 2 is 28. 2x to the 6, I'm going to have to do 2 to the 6, which is 64. And then this is where you have to be careful. This 2 now has to apply to the negative 3 and to the x to the negative 2. So negative 3 squared is negative 3 times negative 3. It's going to pop out a positive 9. X to the negative 2 all squared is now x to the negative 4. Okay, and then my last term comes from here. 8 choose 3.
I'm not reading anything tomorrow. I got to page 60.
Okay, keep reading. I'm almost done. See if you can get to like 65, 66, and you don't have to read on Thursday.
I already don't have to read. I'm on page 60.
You don't have to read on Wednesday. Maybe you don't have to read on Thursday if you get to 80. Ooh. Read the whole book. You don't have to read all week. Just giving you your options. Okay, so the very last term, 8 choose 3 is 56. Here, 2 to the 5 is 32. X to the 5. And then here you have to apply the 3. So negative 3 cubed is negative 27. X to the negative 2 all cubed, x to the negative 6. Okay, so it's a little bit of algebra and arithmetic from grade 11, so you do need to know that. We continue to have 4 terms. They've gotten a little bit uglier maybe. And then the last line will just be a matter of us multiplying our numbers together and doing our exponent law in terms of multiplication. So I'm going to get 256 x to the 8. On this one I have to do 8 times 128 times negative 3. We'll get a negative, which is negative 3072. What happens when I have x to the 7 multiplied by x to the negative 2? You add the exponents. So 7 plus negative 2 is x to the 5. Okay, when you multiply all these, 28 times 64 times 9, I get 16,128. And again, I look at these and say, what happens when I multiply the two x's? I add the exponents, so I get x squared. And then the last one, you multiply, oh, it's going to be negative again, sorry. 48, 384, x to the negative 1. You have a 5 and a negative 6, negative 1. This question is by far much more difficult than anything I would have, Morgan, just a second, much more difficult than anything I would have given you on a test or an assessment, but it encompasses everything you could be given. You could be given a fraction, you could be given a negative, you could be given a very high exponent number. So just be aware. There's one more little example on there that I wouldn't get too overly concerned about, and then the homework. The main goal is, can you do the previous example to this one? Something like x plus 2 to the 4. Maybe x squared minus 3 to the 3. Okay, so more simple sort of ideas. There is quite a bit of extensive homework in this lesson, but I think you can handle it from there. After today, we start getting into a bunch of different distributions. So we've looked at the normal distribution so far. We're going to get into the geometric distribution, the hypergeometric distribution, normal approximation, and something called the binomial distribution, different from the binomial theorem. So we're going to get a bunch of different topics. It's going to seem sort of not continuous, the way we're going to highlight here, highlight there, learn a bunch of different things. They all come together kind of in the end when we do it. Okay, you want to say bye?
No.
Hmm?
No.
No? It's going to stay one.
Bye.
Bye. Ben, you want to say bye? Nope.
Okay. I did actually exactly at chapter 11.
Oh, nice.
Hey, Mommy, move.
Whew, my battery almost ran out.